So now we're going to take a closer look at the ideal gas theory, or the kinetic molecular theory of gases, KM theory of gases. The gas laws gave us the relationships, the observable relationships between volume and temperature and pressure. So these are things that we can measure in the lab. But to explain why those laws exist, scientists go back and they say, how must the molecules be acting? How must the molecules be behaving to lead to these observable gas laws? And that's the theory behind the law. So for example, we've said that the collisions of the molecules with the sides of the container can create pressure. But how fast are the individual molecules moving? And do we see that different types of molecules travel at different speeds? Can we calculate their speeds? And what does that allow us to actually predict about the properties of gases? So we'll see that it allows us to understand the properties of diffusion and effusion of different gases, which we can use, for example, to separate one gas from another, or calculate how long it would take for one particular gas to move through some region of a room or a container versus another type of gas. So we'll be able to distinguish some properties of gases by understanding more about their molecular level behavior. So once again, here's our kinetic molecular theory of gases, and we've talked a bit about points 1 and 2. We're going to come back to those when we talk about some of the properties of real gases that differ slightly from this ideal case. But for this video, we're going to focus on this third point, and we're going to look specifically at how kinetic energy varies per molecule and varies with temperature. So if we're going to look at the average kinetic energy of gas molecules, let's think about what this means. Now I want to point out that for the purpose of this discussion, when I say average kinetic energy, what I'm really specifically referring to mathematically is the RMS, or root mean square, average kinetic energy. That's not going to really be important in our discussions, but it is going to be very important when you go on to your higher level classes, especially in thermodynamics. The difference between a true average and an RMS average, there is a slight distinction there, but because we're not going to use it, I'm just going to say average kinetic energy, and really what I'm referring to is the RMS, average kinetic energy. And another way that I'm going to symbolize that, of course, is this Ke with a bar over it. You're also sometimes going to see in science that we use brackets to signify averages. So you could see Ke average like that, or you might see E sub K in brackets, or actually the more exact variable that we use in physical chemistry for kinetic energy is actually T. So without worrying about any of that, we're just going to talk about average kinetic energy of the molecules. So first of all, when we're looking at the gas molecules in a sample at fixed temperature, we're going to see that they exhibit a broad distribution of kinetic energies. They're not all moving with the same kinetic energy. And that's because as they collide around, the energy is going to spread out, but there's going to be collisions constantly happening. So some molecules will be moving faster, hitting other ones that are moving slower, and so they're going to have this range of kinetic energies. And if we were to plot this, we've seen this before. We looked at this when we were talking about liquids. We can plot the percent of molecules in a sample versus the kinetic energy that each molecule has. Right? And so we get a distribution that looks something like this. It's something like a normal or Gaussian distribution, but with this long tail to it. And the name for this type of distribution is actually a Maxwell-Boltzmann distribution. And we won't look at the functional form, so the function that describes this curve, but there is a not too bad equation that describes the shape of this curve. Just like you would have an equation that describes the shape of a Gaussian curve, for example. And so we can look at a couple of points on this curve. We can say there's our most probable kinetic energy. So we're going to use that little MP to mean most probable. So that's our most probable kinetic energy. because we have the most molecules, the peak, moving with that particular kinetic energy, but that's not our average. Our average is over here, right? Again, we're talking about the RMS, or root mean square average kinetic energy. And because we have this long tail, the average is a little bit shifted to the right of the peak. Okay, so there's our average kinetic energy right there. Maybe I make that a little bit clearer so that everyone sees what I'm talking about. Okay, so there's our average kinetic energy. But again, we have molecules that move slower than the average, and we have molecules that move faster than the average, right, at all times. The next point, which we've made before, is that the average kinetic energy is going to be the same regardless of molecular identity. Okay, it depends only on the temperature, and so we can write this proportionality that the kinetic energy is proportional to the temperature, meaning kinetic energy goes up as temperature goes up. But now we want to say something more precise about it. We want to actually have a set of equations that allow us to describe how the kinetic energy varies with temperature. And for right now, you can go ahead and just ignore this piece here. I'm going to scribble that out. And we're just going to look at the values that we're already familiar with. We're going to say that the kinetic energy of a gas is equal to 3/2 times the ideal gas constant times the temperature divided by the number of molecules in a mole, because this is a value per mole, and we want to look at the kinetic energy per molecule. So we divide by the number of molecules per mole. So kinetic energy equals 3/2 RT over NA. So again, just as we saw in liquids, if we look at the distribution of kinetic energy as we increase the temperature, we see a shift from a more narrow distribution at low temperatures to a broader distribution with higher average energies at higher temperatures. So here's our cold curve and our hot curve, and we see then that with increasing T, we get a broader distribution that's got a higher maximum kinetic energy and average kinetic energy, right? So our maximum kinetic energy is somewhere out here, and our average is somewhere over here on these curves. And this is going to be the same relationship between temperature and kinetic energy regardless of the type of molecule and whether it's a mixture or pure substance. So regardless of the type of molecule, this curve is going to look exactly the same, because kinetic energy, again, doesn't depend on the type of molecule that we're talking about. However, if the kinetic energy of two molecules is the same, and the molecules have different masses, then we can see that their speeds are not necessarily going to be the same. So let's change this, and let's look not only at the distribution of kinetic energy, but now let's look at the distribution of speeds, of molecular speeds. And we'll see that now we have to distinguish which molar mass, which molecule we're talking about. So we could still plot speed versus number of molecules, or percent of molecules. But now if we want to use speed, we're going to have to specify that this is a single type of molecule. So this is for just helium, say. And we could say that at low temperatures, it moves slower on average and has a narrower distribution than at high temperatures. Okay, so at high temperatures, again, the distribution flattens out and the average becomes higher. But we could also plot now a different type of comparison, which is the speed distribution at a fixed temperature. So say T equals 298 Kelvin. Speed is on our x-axis, number of molecules with that speed on our y-axis, and we could plot this for two different types of molecules. So we could see that a heavy molecule is going to have slower speeds on average at this temperature. But to have the same kinetic energy, a lighter molecule is going to have a higher average speed. So the molecular weight of this second molecule, which is distribution is shown in purple, is going to be less than for the molecule whose molecular weight whose speed is slower. So let's say our molecule 1 is SF6, is very heavy, so it's going to be very slow. And molecule 2 could be, say, helium. And so to have the same average kinetic energy, again, because we're at fixed temperature, they've got to have the same average kinetic energy. The helium, the lighter one, has got to go faster. So they've got the same average kinetic energy here, right? Because that only depends on temperature. So that's what we mean when we say that no matter what the molecule type is, it has to have the same average kinetic energy. That means that the lighter molecules must be moving faster to make that true. So let's put that same idea into some mathematical terms to see if we can actually calculate then, based on the temperature, what the speed of a molecule might be. So when we said that lighter molecules must be moving faster to have the same kinetic energy as heavier molecules, we were doing that sort of by intuition, but what we were calling on is Newton's laws of motion. So mathematically, we know that the kinetic energy of a particle or an object has to be 1/2 times its mass times its velocity squared. When we're talking about individual molecules, we're going to use the symbol U for velocity, okay? And we're going to put a little I by each of these just as a subscript, just to say that we're talking about molecule of identity I only, molecule I, where m sub I equals the individual molecule mass. So we're talking about individual molecules, not macroscopic objects here. And U sub I is the individual molecule's speed. Okay, so we're looking at a single molecule at a time here. And we could talk about its average kinetic energy and the average speed of some type of molecule of identity I. So we could rearrange this now to solve for speed, because that's what we're interested in. So the speed, the average speed of molecules of identity I is going to be the square root of the 2 times the kinetic energy of molecules I, the average kinetic energy, over the mass of those molecules. And so that would be how we could calculate it if we knew the kinetic energy. We don't often know exactly what the kinetic energy is. We could calculate it from the temperature, but really what we're interested in is just this relationship that the average speed of molecule I is going to be inversely proportional to 1 over its mass, square root of 1 over its mass. So that means lighter molecule has a faster speed. So the lighter molecules are moving faster. And since we know that the molar mass is just the molecule's total mass per mole divided by the number of moles, we can say that the mass of an individual molecule is just going to be its molar mass divided by the number of moles, the mass of a gas is going to be its molar mass divided by the number of moles. So we can also say then that the average speed is going to be proportional to 1 over the molar mass, which is a number that we're more familiar with than the mass of, say, individual molecules. And then again, we know that since kinetic energy is directly proportional to temperature, then the speed of a gas molecule is going to be inversely proportional to the square root of the temperature, is going to be proportional to the square root of the temperature, or we don't even really care about the square root there because it's a proportionality constant. It's just proportional to temperature. So temperature goes up, speed goes up. and it's inversely proportional to the mass. Once again, to keep this video from getting too long, I'm going to ask you guys a conceptual question, and then we'll start another new video to go through the examples using the kinetic molecular theory of gases. So the question is this: suppose you have a container filled with only O2 gas at fixed temperature, we'll say. Which of the following statements is false? You can pause your video and try to answer this question. So based on what we've just talked about, we know that there has to be a distribution of kinetic energies regardless of the identity of the gas. So A is clearly false. All of the gas molecules do not have the same kinetic energy. We have that distribution of kinetic energies. The average kinetic energy of the gas molecules increases with temperature. We know that that's true. The average speed of gas molecules is related to its kinetic energy, so we know that that has to increase with temperature as well. And there are gas molecules that move slower than the average and faster than the average. Both of those are true as well because we have this distribution of speeds. Okay, so the next video is going to be examples of calculating molecular speeds and what that tells us about diffusion rates and effusion rates.